Hello everyone, welcome to our webinar this afternoon. We are going to wait a few minutes so that everybody can join us. You are already 25, and for those who are already here, can you just tell me please if you can hear me well? You have a questions part in the interface on the right where you can write, please. So good afternoon to everyone. We are going to start gently so that people can join us. Today, we are going to speak about how to reduce risks in the management of contaminated sites. Thank you for joining us for this webinar session. In a few words, why do I speak about that today? So I'm Claire, I'm working in geosciences, mainly in contaminated sites, but it can also be in other environmental fields. And I'm applying geostatistics for those sectors. And risks and contamination computation, computing volumes, computing mass are really something that I'm doing quite daily. And knowing that we have lots of uncertainties in all our computation, how do we manage to keep the risks as low as possible is really an important question. So we're going to be together during about half an hour, but in fact more than that, I think. There will be a presentation part, the first one, and during all the webinar, you can write some questions in the interface of GoToWebinar. Your microphones are all muted, and I will answer your questions at the end. And I will also let you a few minutes at the end of the presentation to write other questions if you have, or if you want to be very focused on the presentation and keep your questions for the end. And tomorrow or in the coming days, you will also receive a link if you want to have a replay of this webinar. It will also be available. So what we're going to discover today is how to manage those risks in the management of contamination, and how can we calculate in a rigorous way the soil volumes and the pollutant masses that we have to treat to respect some remediation threshold. And more than that, we would like to have some methodology that would be quite quick so that we can evaluate several remediation scenarios according also to the uncertainty and so to the risk of leaving some pollution in place. So we are going to see how we can do that. And my starting point is going to be something that I've presented in my last webinar in November. If some of you already have attended this webinar, I don't know if you remember, but we were speaking about uncertainties and the uncertainties that can occur in all the environmental data cycle in the context of managing contaminated land. If you look at all those steps here in the circle, in the previous webinar, we've seen that each step can generate or be influenced by uncertainty, that there are many types of uncertainties. And today, we are going to focus more on the left part, all the decision making and communication of those results in an uncertain context, and so how we can reduce the risk in our decision making, knowing that we have uncertainties in our computations. The presentation today will be divided into 3 parts. The first one will be a bit of geostatistics, some reminders for some of you and discoveries for others. Then a short video presenting you a solution to see all those mass and volume computations. And at the end, I will show you how you can do all of that in our software, Cartotrack, where we have developed a completely new workflow to compute those volumes and masses of contamination. So first, the recipe of geostatistics in a few words, really a summary of what we do. The ingredients, first, what do we need? We need to have data, and at least a part of data that are numerical data, so soil samples or acquisition of numerical data on the site. From those, let's say, samples or numerical values, we are going to build a variogram, one or 2D variogram or 3D if it's the case. And this is really the basis of all geostatistics. The variogram is going to describe the spatial continuity of our phenomenon, and it will really be a translation of the spatial behavior of the contamination on the site. And we are going to use this variogram function, this model, to build estimations afterwards. The last ingredient is to choose a grid, a mesh size, both horizontally and vertically if you work in 3D, and also to choose a neighborhood when estimating one particular mesh. How far do you go to search for neighbors? With all those ingredients, we are able to make interpolations, geostatistical interpolations in this case. Two big families. The first one is the kriging. You have an example on the left, and then the simulations. So in our case, it's geostatistical simulations, a bit like Monte Carlo simulations, but using the variogram and to be able to build different scenarios. So the kriging here gives an estimation map, which is the most probable value for each cell of the grid. So this is the first map you see on the left that gives you the best estimate for concentration. Associated to it, we have an uncertainty map, knowing that the uncertainty will increase when we are far from the data. So this is the first family of results, and we can also build geostatistical simulations. And what we're going to see today comes from is available if it's possible to compute if we have done geostatistical simulations before. So simulations, the aim is quite different. We build scenarios. All the scenarios, all the maps you see here are have all those same probability to occur. And between different maps, we have different scenarios that respect the samples and that take into account the spatial variability thanks to the variogram. So today we are going to use those simulations results and know and see what we can do with those maps. So now from those simulations, what are we going to do in this context of managing contamination in soils? I'm taking again the different simulated maps. Here I have an example with 5 maps, but you see the dots. We have, in general, at least 100 simulations. So 100 maps of concentrations here. And you see the legend going along with the maps. And we are going to apply a threshold to define the areas that are contaminated and areas that we can consider as clean. So what do? We cut each simulation. Here I've taken an arbitrary threshold at 150. And what do you see? We have blue and red then on the maps below. And what we clearly see that some areas of the site are always blue, others are always red, but there are quite a lot of meshes, in fact, on the grid that are sometimes blue and sometimes red. So it means that we have uncertainty. There are areas where we are pretty sure that it is contaminated, areas where we are pretty sure it's not contaminated, but we also have some areas where there is some risks, and we are going to quantify this risk. So what do? For each cell of the grid, we are going to count the number of times the grid has exceeded the threshold over the 100 or n simulations. And this is the map we get at the end, which is the probability to exceed the threshold map. So now the color, the legend, is between 0 and 100%. So on this map, you see that there are parts that have less than 10% of chance to exceed the threshold in dark blue. We have parts in orange and red where there is more than 70% of risk. And we also have parts between 30 and 50 or 60% of risk, where in fact we really don't know if we are above or below the threshold. Knowing that, we're going to manage this risk, and we can easily build different scenarios. For example, with different level of risks. Here you have isolines, for example, from 20% to 50% of risks. Obviously, each risk will lead to a different area or volume if you are working in 3D, and also to different costs. And we are going to decide, and it's going to really to be a balance between costs and acceptable risk to leave some contamination in place. If you cut this map at 20% here, then you get the area you should treat to remediate for this threshold of 150. So this is the way we can handle the risk and accept a risk to leave in place some contamination. If I do that with 20%, it means that in all the white parts here, I will never have more than 20% of risk to exceed the threshold. The maximum risk that I have a contamination in place that is left after the treatment here is 20%. So this is going to define my area or my volume to remediate. And then for each cell on the grid here, since I've done a lot of simulations, I don't know exactly the concentration, but I have a distribution of possible concentrations for each cell. So if I want to compute the total contaminant mass that I am going to remove, I also need to take into account this uncertainty, and I will be able to compute the mass plus a confidence interval around this probable mass that will be removed in this defined area. So this is what we are going to see after that interactively. To explain perhaps a bit more about the decision making with uncertainty, two small graphs. The first one with two estimations, the blue diamonds. This is the same estimation, but in both cases we have different uncertainties. On the left we have a small uncertainty, much higher on the right. What is the consequence? If we take the threshold with the red line here, the consequence is quite clear. It's that on the left, sorry, we have no risk to exceed the threshold, because even if we take into account the uncertainty, the upper bar will never be above the threshold. Whereas on the right, we have an estimation that is lower the threshold, but knowing that we have some uncertainty, in fact, if I do a lot of simulation, the mean is below the threshold, but there are some simulations, and here about 30% of the simulations that will be higher than the threshold. Knowing that, I have to take decisions. How to do that? Another graph here with different probabilities to exceed the threshold. So the same blue diamonds with which are the estimation. So here we have different estimations and almost the same uncertainty everywhere. What should we do with this? There are parts where it's quite easy, where we are going to declare that it's not contaminated for low risks. There are parts where the risk is really high. We are going to declare them as contaminated with no doubt. And the big question is going to be the orange part here, where should we put the frontier on the risk to declare that it's contaminated or not contaminated. A bit more than that, it can also be areas that would be quite interesting to be sampled again, because it's it corresponds to areas where the risk is intermediate and where we don't really know if it's contaminated or not. So it could be also areas where it's interesting to collect some additional samples. What do we have to explain and to communicate about our results? The first thing is going to be 3D views. For example, here we have an example of grid, 3D grid here, where we have considered different waste routes with different thresholds, and all the clean or declared as clean meshes stay invisible, and you only see the mesh that should be sent or treated for the different waste routes with the 3 colors. Corresponding to this, we are able to compute number of cubic meters that is exceeding those thresholds. Here you have an example with a risk of 20% in bold. That would correspond to 16,000 cubic meters. In those 16,000 cubic meters, we have concentrations that have been simulated, and so in those blocks, we are able to compute also the mass of contaminant that is going to be removed. And this is really interesting because with that, you are able to compute a percentage of mass removal, for example. In this case, we have an example where the probable mass is going to be about 8.8 tons. But we're able to take into account the uncertainty and say, for example, that we have a confidence interval at 90% comprised between 7 tons and 10.6 tons of pollutant. All of this can be done with different parameters, for example, TPH and BTEX here. And for each, we can have the remediation volumes, the total volume that is going to be the union of all pollutants, and we have the mass that is going to be removed for each pollutant. And if we continue, we can go one step further and start to define an excavation plan if this is what is planned for the remediation. So we can go up to this excavation plan that is going to define so the remediation volume plus the accessibility volume to get a total excavated volume. And we also get either the elevation or the depths until we should excavate for each grid mesh. So this is what is going to be possible in Cartotrack. This is the short video where I will show you the different steps a bit more interactively. And after that, we will move to the demonstration. So what we've built, it's a workflow that will enable you to decide and to balance between environmental risks and costs. So we've tried to make a complete and quite intuitive workflow. Starting point, the samples, concentration samples. From that, we build a geostatistical model and we generate contamination maps. After that, we can play with different thresholds or with different risks for one threshold, thus defining volumes and costs, and compare really easily remediation, different remediation scenarios. We can also handle waste routes and be able to define the different volumes. Last thing that is, sorry, going back here. Last thing that is possible is to take a Pareto approach, trying to compute the mass reduction, so the efficiency of decontamination regarding the remediated, the percentage of the volumes that has to be remediated. And the Pareto approach would say that you can remove 80% of mass in 20% of volumes, even if we know that it's not happening like that on all sites. But we are also able to build those curves that can also help you to define thresholds if they are not defined beforehand. Last step, the excavation plan that you can also refine by hand if you would like to excavate those mesh that is alone. We are able to treat several pollutants at one time, and we can also divide the volumes and mass computation into different soil layers. So I'm going now to show you the workflow directly. That will certainly help you to raise questions too. And let's go for a demo. So I'm going to take the same example. So I have quite a lot of samples on this site, but it's not compulsory to have so many boreholes. What I've done, I've built a complete geostatistical model. And for example, I have a kriging results. So this is the kriging map in 3 dimensions. And I can choose the mesh. So here it's something quite fine with a 1 meter mesh. And I also have a second model more dedicated to excavation, where I've taken big blocks of 15 by 15 by 1 meter. So this is what I'm going to use here in the volume and mass workflow just afterwards. The colors that you have here correspond to the probability to exceed this threshold of 100 here. And it's going to be the beginning of all the story of the volumes and mass workflow. We have imagined 3 different ways to go through this workflow. Either you have 1 threshold per parameter, or several thresholds per parameter. We've called it a waste management plan. Or there is no threshold that is predefined, and it's efficiency driven and what we call the Pareto approach. I'm going to show you two of them, the efficiency driven first, and then we will move on to the waste management plan, knowing that this one is just a simplification of this one. So regarding the efficiency driven, the first thing when I'm in this workflow is to choose the domain I want to consider. And I would like to take one area. I'm able to take several areas at one time or several layers at one time and combine them as I want. For each domain here, so it's here I've taken the first zone between topography and the bottom I have defined. And for each zone, here I only take one, I need to choose the contaminant. Here I have TPH and BTEX, for example. The first step is going to be common to all the ways I have to go through this workflow. First step is going to tell me how many tons I have of contaminants on the site, just as if I had a threshold of 0 or at the quantification limit. So what does it tell me? It tells me that I have about 16 tons of TPH, for example. But knowing that I've done simulations, I have an uncertainty about those concentrations. So I have an uncertainty about this total contamination. So in fact, it's about 16 tons, but I'm also able to tell that I have a confidence interval, for example, at 90% between 13.5 and let's say 18 tons for TPH, and the same for BTEX. After that, I have this Pareto graph that we've built, which is driven by the mass reduction we would like to get. So on those curves, you have all the mass reduction, and the more you add blocks, the more you remediate, the more you remove some mass. But the smaller the threshold you will need to take. And I have this for both contaminants. And what I'm going to choose here, so I can play with the quantiles I would like to see. I can add other quantiles, for example. But what I'm going to take is, okay, I would like to reach a remediation efficiency of 75%. And since I have several contaminants, I also see what it brings me to remove 75% of THC. And in this case, I will also remove more than 75% of BTEX. But I would like, if I like to reach 80%, I can also ask 80% of BTEX and know what's happening on this graph. So this can help you to define threshold, for example, or you can continue with this and just say, okay, what I want to remediate, and here you have the volume preview that you should remediate to reach this percentage of mass reduction. So this is the first step. I can continue up to the excavation, but I'm going to show you the excavation with the waste management plan just afterwards. I'm closing this and starting again with the waste management plan this time. Taking the same at the very beginning, the same domain and the same contaminants. It means that I have the same results here, always the 16 tons of TPH here. And the next step here is to define different waste routes. I can give the names I want. I can add as many waste routes as I want. The only thing is that I need to previously have computed the probability of exceedance for the thresholds I want to consider. And it will be an iterative way to do that. And I will always start with the highest routes, deciding of a risk for this route, sending some cubic meter in this first waste route, A here, and then on what is remaining, starting with the waste route B, etc., etc. So it means that my waste routes have to be defined from highest to lowest thresholds. It will be a bit more clear just after. I have to take the thresholds in the decreasing order here. Here I'm taking all the pollutants for each waste route, but you can have some waste routes that don't have any criterion, for example, for one of the contaminants. And then I'm going to start with the first waste route A, which takes into account the highest thresholds. And what do I have? So I have this volume preview here, directly linked to the probability to exceed the thresholds. And depending on the risk I take here, it will give me more or less cubic meters to remove. So here it's with the risk of 50%. If I take these risks, it means that in the blank parts here, I will never have more than 50% of risk to exceed the threshold. But I can change this risk, knowing that if I lower the risks, the number of cubic meters will rise. And I see the corresponding cubic meters on the graph here. And this is a very classic curves shape where it won't cost a lot of cubic meters and euros or whatever for high risks, let's say. It doesn't cost a lot to take 30 instead of 40% here, for example, but it's going to cost a lot more for each percent we add or we lower for lower risks. Here you have taking 10% or 5% less risk will cost a lot more than here. So it's going to help you to make, if you want different scenarios of risks, see what it costs afterwards, and see what are the cubic meters you're going to send in this first waste route. Let's say that I'm taking 30% here, for example. So these are going to be all the cubic meters I have to send to the first waste route. With this risk, I'm able to compute the kilograms of contamination I have in those blocks for each contaminant. For TPH here, I have almost 16 tons, so quite a lot of the total quantity of TPH I have on the site, and almost, and 115 over 200 for BTEX. And sorry, it's 8 tons over the 16 for TPH. So in this first waste route, I'm going to send a bit more than 50% of the total mass of contamination over the site in about 10% of the volumes, which is we have 25,000 cubic meters over an area of 230,000 cubic meters. And I have the uncertainty of contaminant mass for both pollutants. After that, I'm going through the second waste route. So this time, I'm considering only what is left after I have sent the soil in the A waste route. So I'm working on these soils, and in those soils now, which risk do I take to send soils in my second waste route? Let's say again like that I take 30%. I'm doing the same. I get new volumes that are really much smaller. I have 10,000 cubic meters for this second waste route corresponding to those grid cells. And it's the same for computation of the masses. I get the mass that I'm sending to this second waste route, and I'm going to do the same with the last waste route, and finally get all the blocks colored by the waste routes they should go in. And knowing that in the other parts, it's corresponding to blocks that have less than 30% of risk to exceed thresholds. Final step, I have a summary here of all the kilograms I've sent in the different waste routes, the total remediation volume. I'm able also to fix a density of soil, and if I want a bulking factor, so that I have a total remediation volume and a total bulk volume if it corresponds to excavation. Final step, the excavation plan. So I have this waste management results before, and here you see that the excavation plan is the complementary of those blocks, plus the accessibility volume. For example, here you have quite a lot of accessibility volumes to reach the contamination that is really at the bottom of the domain. And I have this map here in 2D, which corresponds to the elevation here that I should reach to remove all the remediation volume I have decided just before. When I save those results, I get them here. I have my waste management plan that I can show again in 3D. And I have this excavation plan too. And the particularity of this excavation map is that I'm able also to display it in 2D. And in this case, I will just get for each mesh the depth or the elevation. I have the choice between both. Depth or elevation I should reach to remove the blocks here. So basically that's what is offered by the workflow. This workflow is available in the last version of Cartotrack, available since July, so maybe some of you already have it and use it, maybe. In this case, we would be very happy to have your feedback. And for others, we also are available for questions. And if you want to try it, we can also provide you with a Cartotrack POC or evaluation based on your data. Well, that's it for the presentation part. I will give you some minutes to ask and write questions in the dedicated part of GoToWebinar interface. Take those few minutes to speak a little bit about GeoVariances for people who don't know us. So GeoVariances is a global provider of geostatistics based solution. We are mainly based in France, but also have different offices worldwide, in particular to address the mining sector. We are more than 35 years old now, and we have some partnerships with different research centers like the Paris School of Mine or the University of Neuchâtel in Switzerland, for example. And what do we provide? We try to build a global solution and a very flexible offer and we try to adapt really to your issues and what you are able to do, what you would like to do, etc. So the first thing, and you've seen a part of it, it's the software solutions. And I've shown you a part of Catotrack, but there is also Isatis Neo. Maybe some of you know Isatis Neo, which is the big geostatistical toolbox. For some clients, sometimes we build libraries on demand, so development on demand. And what I personally do quite a lot, it's training courses to train you in geostatistics and the software use, and also providing you consulting and mentoring services. So we provide mapping, modeling, volumes and mass quantification, etc. Trying to answer the best we can do for your issues, and trying to integrate our workflow in your company process also, which is which is really important. How do we have the input and output of our software? To go further, just a few dates. The next sessions for the trainings, we have a seminar of 1 day in May, and a training session using Catotrack, and also, so it's about half-half between geostatistics in theory and use of Catotrack. There is another session coming during spring. I've not taken the next date here. And we can also build on-demand sessions, and on our internet site we have a complete catalog, and you can also find other sessions, in particular if you come from the mining sector, or if you are, for example, from the hydrological sector or radiological. We have other sessions using either Catotrack or Isatis Neo. That's it from me. And now I'm going to read your questions and try to answer them in the order. Thanks a lot for your attention, and you will receive just after the webinar an evaluation form that I would be very glad that you fill in to have your feedback about the webinar. And now let's take the questions. You can still write some questions if you want. So there is a question about trying to attempt application of geostatistics for the estimation of critical geotechnical parameter at ground investigation stage. Is there any customized module of Isatis Neo for geotechnical projects? We are doing, I'm not a specialist of geotechnics, but we are doing geostatistics in the geotechnical field with Isatis Neo quite a lot. So it's not a dedicated software for geotechnics, but we completely use Isatis Neo for geotechnics. This is the only question for the moment, so don't hesitate. Some of you already know us and think that this new edition is an interesting tool, so thank you very much. I don't know if you already have the new version then. We've tried to build something quite relevant, at least. So there is a question, yeah, about the quantity of data in my example. I do have really a lot of boreholes in this example. So the question is, how does it work if data is limited? You can build a variogram, so there is a limit. You cannot build a variogram with 10 samples. We often say that below 20 samples in 2D or below 30 to 50 samples, not boreholes, in 3D, it's difficult to build a reliable variogram. After that, depending on the shape of the variogram, it can show you different situations, more or less erratic. But the less data you have, the bigger the uncertainties. At the end, you will get bigger uncertainties. But what we try to promote too is that even if you have a limited number of samples, you can try to build a geostatistical model, see what happens in terms of uncertainties. Maybe there will be areas that will be clearly contaminated, other that will be clearly clean, and see what happens in the very uncertain parts. And the problem is if those uncertain parts are close to the thresholds. But having this first model, even based on a limited number of samples, may enable you to plan additional samples and see how you can handle those uncertainties and therefore limit the risk afterwards. Is it taking the uncertainty from sampling? In fact, the uncertainty during sampling will be seen on the variogram. There is a part when it exists called the nugget effect. And the nugget effect, in fact, is if I understand well the question, can reflect the fact that we have a high uncertainty at small distances. And this high uncertainty at small distances can sometimes come from a problem or uncertainties during sampling. And if you have a nugget effect on the variogram, it will lead to more uncertainty in the results. So it's a way to reflect this uncertainty and incorporate this uncertainty of the sampling in the results. Yeah, another question about sampling strategies, saying that in most cases, a spatial distribution of sampling locations does not cover all the sites. It's really something we encourage. Do not focus only on already known contaminated areas, because it's really dangerous. And it's really often that we discover contamination in parts where we don't thought we have contamination. So the idea is to, the main idea, but sampling would be a complete webinar or more than a webinar subject. The idea is to have a basic sampling everywhere, maybe with a loosened mesh, and to refine in some parts if it makes too many boreholes to sample all the site, but at least sample also locations where we don't have anything, because there is also bad surprises during remediation works. Is it possible to import rigging made in Surfer software? No, because we really use the results of Cartotrack, and in Cartotrack the particularity is that it's not a black box. We have different variogram models, and we are really able to build what we want. I think Surfer is only 2D, whereas we also have 3D models. And the kriging capabilities, so the kriging in itself are almost the same in Surfer and Cartotrack, except that in Cartotrack we really work, it was not the subject of the seminar, but we also have a very large part dedicated to quality control of the data. to regularization of data, if we have different lengths of samples, do we have outliers that we should remove, etc., etc. So we have a lot more capabilities of sampling, detection of outliers, quality control, taking into account different lithological layers also. And regarding volumes and masses, the workflow I've just shown you, it's based on simulations. So it's not based on kriging, and I need to have simulation results which are not offered in Surfer. For the moment, I think I've answered all the questions. So perhaps a bit more about import and outputs. The samples that we import need to be in CSV or XLS files. We can visualize a lot of formats for vector and raster maps to bring context. And in output, we can export the CSV grids. So all the results that have been computed can be exported in CSV. And all the images can be exported. And for 2D maps, we export them also in a geo-referenced way. And there are also different formats, and we take into account all the possible geographic systems for the import. There is a question for multiple contaminants within a site, saying that the simulation work will be huge. What do you suggest to reduce that? In fact, the simulation work could be okay. The problem is that if you have really a large number of contaminants, you will have a lot of quality control, variogram building work. What we usually do, so it depends of what you call multiple contaminants. If it's 4 to 5 contaminants, it's really easy to handle them with the multivariate variograms, and I can show you just after how it works. But if you speak of 30 or 40 contaminants, obviously you won't build a model for each of them. It means that usually we make some statistics, exploratory data statistics, trying to see what are the problematic contaminants, because sometimes not all of them are able to exceed thresholds or lead to pollution. So we usually reduce a lot the number of contaminants looking at the values. And we also reduce the number of contaminants looking at the correlations between them. If we have very good correlations between pollutants, we can take the pollutants that really drive the contamination and just check that handling this contaminant will also remediate some other contaminants that are really well correlated. But I can show you this in Cartotrack. I only have 2, but so there are different ways to handle multiple contaminants. So this is the workflow dedicated this time to the 3D kriging or 3D simulations. First, I need to choose the zone I would like to consider, the layers I would like to consider, and the contaminant, plus other options. This is an intermediate steps of regularization. And here, yeah, it's nice because it's what I've done. In fact, I'm building, so either I build one variogram model for each contaminant, or I'm able to build a multivariate model and This is something that is not possible in Surfer, for example. And here I'm only building one model for TPH and BTEX. So I have an horizontal variogram for TPH here at the top. I have an horizontal for BTEX at the bottom. And I have what we call a cross variogram describing the correlation of both contaminants here. And these are the horizontal variograms. So here I have a distance of more than 100 meters. And I also take into account vertical variograms, and this time we only have a few meters, so the length of the boreholes. But it's the same vertical variogram for TPH, BTEX, and the cross variogram. And if I compute this, so this is the last step where I choose the grid resolution, where I choose the number of neighbors, and where I choose also the thresholds for my different contaminants. It's not costly in terms of computation time to choose a lot of thresholds. What is costly will be the number of simulations you take, and it depends on the size of your site and the grid resolution you have here. But then in this case here, I don't know how many meshes I have, but it takes less than 2 or 3 minutes to compute the 100 simulations for BTEX and TPH here in this case, on a good computer. And I don't know if I've answered everything. I think yes. There is a remark about the uncertainty about the variogram that should be highlighted. Yeah, on the variogram here you see the shape of the variogram, and the fact that you have or not a nugget effect will describe the spatial behavior and the higher or lower variability you have in particular at small distances. But we're not able to speak about everything in one webinar. If some of you would like to have a look at the previous webinar on uncertainties, it's available on our website if you want to look at it. And I had some considerations about the variograms and the uncertainty that you can see on the variograms. Maybe it can answer some questions too. Well, I think that's it. Don't hesitate to write us some emails or really answer the evaluation form if you have some other questions or would like to try Cartotrack or even Isatis Neo that I haven't shown. I'm still staying a few minutes here, 1 or 2 minutes if you have questions. And otherwise, thank you very much for your attention, and I hope to see you in or read you in some emails in the coming weeks. Well, thank you and goodbye. Have a nice afternoon.